lesson 3, and we're on day 3 of the first unit, and we're going to look at a number of graphs first before we summarize. So the first one, not to insult your intelligence, but it is a line. So we have a line from grade 9 where we have the equation given to you, and they also put that on the graph, which is a good strategy. Our domain, we haven't seen this notation before, but it says that n, the number of copies, goes from 0 to 1500. So it makes sense. You can't have a negative number of copies of a yearbook, and apparently you can't have more than 1500. Our range, so that's the acceptable x value, sorry. Our range is our acceptable y values, and it is total cost, so money. So our range is from 8,000 to 14,000. So one of the questions says, in the equation C equals 8,000 plus 4n, explain what the numbers 8,000 and the 4 represent. So from grade 9, we know that the number that stands alone is called our initial value. Our initial value on the y-axis would be our initial cost. So it's going to cost us at least $8,000, and that makes sense when we look at our range number, 8,000 being the smallest. It means to get started, it's going to cost us $8,000. I don't know what that would be to set up the printer, whatever. Started at $8,000. And then it's going to go up from there depending on how many copies. The number 4 is what we called in grade 9 our slope, or our rate of change. And that would be $4 per n, which is the number of copies. So apparently it's going to cost us $4 every copy. B, describe how the graph would change if the numbers 8,000 and 4 were to change. So if the 8,000 were a 6,000 or a 10,000, that initial value would be higher or lower on the y-axis. If the 4 were to change, that is our rate of change. That means the copies would be more expensive or less expensive, and that would make the graph steeper if it were greater than 4, or less steep if it were cheaper. Less steep, help if I could spell. If it were less than $4. Don't worry about the symbols so much. Let's just get the idea. Does this graph of the function, notice that it is a function. I could draw a vertical line anywhere along that line and it would only hit in one place. Does it have a maximum point and a minimum point? Well, technically, it keeps going on and on forever, except that our range says, we're going to stop right here. We're not going to make any more than 1,500 copies. Maybe they only have 1,500 students. So it appears that our maximum value would be almost $15,000. What is it, 10? 13,000, something like that. It does have a maximum. When we do the 1,500 copies. If we didn't have an end value on the domain and we just kept making more and more yearbooks, we could make more and more profit. But we do have a maximum because of the domain. The minimum is 0 when there are 0 copies. That's going to cost us $8,000, but it's the minimum profit and a minimum value. A second function that came from grade 10 is a parabola, or a quadratic function. So we have a graph and we have an equation, and we can see that this is a function. Anywhere that I were to put a vertical line would only hit that graph in one place. We have an equation with negative 0.49 and a 9. We have our domain and range laid out for us. So it says the time, the acceptable x values, or in this case t values, goes from 0 to 4.2. That makes sense to not have time be negative. And we have an ending place where that ball, or whatever it is, falling object, hits the ground. So that's the end of our story. The range is the height, and its lowest point is 0 when it hits the ground, and its highest spot is 9. Right here, let's answer the questions. Number 2. What was the initial height of the object? The initial height is always on the y-axis, and it is 9. Units are meters. How long did it take for the object to hit the ground? It took a little over 4 seconds. So less than 4.25, so 4.1 seconds. Describe how the graph would change if the initial height were different. If the initial height were different, it would be higher or lower on the y-axis. And we see that number 9 in the equation right here. That is our initial value. The negative 4.9 is not quite a slope because this is a parabola, not a line, but it does describe the shape and the steepness of this graph. Let's look at another one. Number of hours of daylight in Ottawa during a 2-year period. This is a new type of graph. The equation is enough to make us squirrely, and we have a domain and a range laid out for us. So the n, which is the number of days, So the acceptable x values, or n in this particular case, goes from 0 to 730. That should make sense to us that time doesn't start before the beginning of our story, and we're talking about a 2-year period. So our domain is between 0 days and 730 days. The range is the acceptable y values. And if we look at that funny curve, it does lie between 8.8 and 15.6. So our range has a lowest spot and a highest spot. We're going to answer A and C. We're going to ignore B so that I don't make anybody cry on the 3rd day. 3A, determine the greatest number of hours of daylight. The greatest number is 15.6. I got that rather quickly from my range because somebody had already done the work at looking at the graph carefully and seeing that it hit at 15.6. Determine the least number of hours of daylight would be 8.8. And I got that from the range as well. So my minimum and maximum value comes from the range. Determine the mean number of hours of daylight. So your mean is your average. And in the middle of 8.8 and 15.6 is the number. How on earth do I get an average? Well, I add them together and divide by 2. And the middle number would be 12.2. Interesting. And so the middle of that curve would lie right in there. It's saying on average in Ottawa, in a day, you'd get 12.2 hours of daylight. So that would be in May and October. Okay, C. A location further south than Ottawa has a lesser variation in the number of hours of daylight. describe how the graph would change if it was drawn for this location. So if you don't have such extreme days, so you are in North Carolina and your days aren't quite so extreme, our graph would have a lesser maximum and not quite such a minimum. So maybe, if you can see on the graph here, it would just have a smaller range of values, if that would make sense. It would affect those numbers. So we've looked at 3 of the 4 basic graphs. We looked at what we call sinusoidal or periodic. So this first one, something that goes on and on over and over and over again, is called a periodic function. We're going to look at that later on in the course. The one that we did not do an example of is called exponential growth, and it is where something increases more and more rapidly as time goes on. So something like bunny rabbits or money and so on would be exponential growth. The last 2 would be quadratic. That is from grade 10. And the line, which would be grade 9. We're not going to spend as much time on the line. I think you're all experts, but we are going to start our course with a good look at the quadratic. It can be easy from a graph to know which is linear, exponential, periodic, or quadratic, but sometimes we don't have a graph and we're working from a table of values. So it can be a helpful strategy to look at first and second differences to tell us if we have a line or a quadratic. So let's look at these 2 and see what happens. The first one, when I look at my first differences, I'm looking from the numbers 7 to 12 and I'm subtracting. So the key phrase is differences. And I know many of you know what you're doing here. 7 subtract 12 is -5. So I'm going down by 5 that time. The next subtraction would be 5 subtract 7. I've gone down by 2. 6 subtract 5. I've actually gone up by 1. 10 subtract 6 is 4. I've gone up by 4. My first differences are not the same. I do not have a line. That's all I know for sure. Second differences. I am looking at the numbers -2 and -5, and I am subtracting them. That can be a little trickier. Make friends with your calculator. -2 subtract -5 is +3. So I've gone up by 3 values. 1 subtract -2 is also 3. Interesting. 4 subtract 1 is 3. I've gone up by the value of 3 each time. My second differences are the same. That tells me it is quadratic. Second table. Second example. I'm doing my first differences by subtracting subsequent values. So 8 subtract -2 is 10. -2 subtract 8 is -2. Well, that's just weird. 8 subtract -2. Crazy. You can see that your y values go from -2 to 8 to -2 to 8 to -2 and on it goes. This is a regular pattern. This is a periodic. My first and second differences don't help me so much. I can see that I'm going back and forth between values. 2 more. This third table, I'm subtracting values to get my first differences. Okay, -4 subtract -9 is 5. 1 subtract -4 is 5. 6 subtract 1 is 5. 11 subtract 6 is 5. Generally don't trust my arithmetic, but my first differences are all the same. That tells me I have a line. We're going to look at the last one. You could make the assumption that it's going to be exponential, but we're going to have a look at those values anyway. I have gone from negative or 32, sorry, to negative 16, so I have gone down by 48. From 8 to negative 16, I have gone up by 24. From negative, sorry, 8, sorry, down to negative 4, I have gone down by 12. So we take our values and multiply by negative a half. As we go down that table, if we are multiplying over and over again by a certain value, that would be exponential growth. Last way of looking at these equations, we've looked at graphs, we've looked at tables of values, and lastly we could look at a description. The first one, Nabilia takes a taxi to the airport. She pays a flat fee of $5 and $1.50 for every kilometer traveled. We could write it as an equation. Her amount paid would be $5 and $1.50 for every kilometer traveled. But even for the description, we can see that we are going up by the same amount every time. Our first differences would be $1.50. This one is linear. The second one, your boss pays you $1 for your first day of work. On your second day, he pays you twice the amount of the first day. On the third day, he pays you twice the amount of the second day, and so on and so on. You're going to get rich fast. That means he multiplies by 2 every time he pays you. So you started with $1 and you multiply by 2 over and over and over again. That is exponential growth. C. A soccer ball. Did lots of those last year. A soccer ball is kicked into the air. It rises to a maximum height of 12 meters and then falls back to the ground. If you saw a graph, you would kick it and it would go up to a maximum and back down again. The force of gravity working on it. We would have a parabola or a quadratic equation. The pendulum on a clock swings back and forth and back and forth, and our y value is the distance from vertical. So if you have something that goes over and over again, and you could graph it so that it looks like close to vertical, away from vertical, close and away, over and over again, that is a periodic function. Lastly, you roll 36 dice and remove the dice with 1 dot showing. You roll the remaining dice and remove the dice with 1 dot showing. Over and over again, we keep removing the dice with ones. You have a 1 in 6 chance of losing a die. Chances are pretty good that you're going to keep 5/6 of the number of dice that you have at any time, over and over again. If you multiply by the same number over and over again, you have exponential growth.